Hello everyone, welcome to Simplified Computer Science Concepts by Professor Rutuja Kadam. Today we will be learning Lamport's mutual exclusion algorithm. So let us start. So what is this mutual exclusion in distributed systems? Prior to that, let us see what is mutual exclusion. Mutual exclusion is a concept wherein a critical section, or we call as a shared resource, it is shared among various processes. Now already that particular shared resource is used by a particular process. At the same time, some other process, let us say P1, wants to enter into that critical section. However, if the shared resource or that critical section, if utilized by some other process, P1 cannot enter into the critical section. So the concept of mutual exclusion says that for at any given point of time, only one process can execute into the critical section, or only one process can utilize the critical section. Now how about the mutual exclusion in distributed systems? So let us say this is a distributed systems, or let us say this is a system wherein it has a own clock and it has its own shared memory. But in distributed systems, we do not have shared memory and a same clock because the systems are geographically apart from each other. That is why the concept of shared memory and a local clock does not work. So obviously the mutual exclusion techniques such as semaphores will not work in distributed systems as it requires shared memory concept. Hence, an approach based on message passing is used to solve mutual exclusion problem because the interprocess communication that is used in distributed system is message passing. So, we have to follow an approach which is based on message passing. So, what all solutions are there for mutual exclusion or to achieve mutual exclusion in distributed systems? So, obviously the solution will be based on message passing. So, there are basically two types of algorithms that are there to achieve the mutual exclusion. The first one is non-token based algorithms wherein the message passing or the synchronization takes place with the help of timestamps, and these timestamps are passed using messages. So the algorithms are Lamport's mutual exclusion algorithm and Ricard-Agrawala algorithm. And in token based algorithms, there is a Raymond's tree algorithm and Suzuki-Kasami algorithm, wherein a token is nothing but a holder, or we can say it as in a real-time example, it is a ticket which is given to a process who is already into the critical section. Once it exits the critical section, this particular token will be transferred to any other process which is requesting for that particular critical section. So the process who has that token is the one who will enter into the critical section. This concept is mapped to a real-time concept of movie tickets. So if the person has the movie ticket, then only he is allowed to enter into the cinema hall. So let us see the general system model before starting Lamport's mutual exclusion algorithm. So basically there are three messages that are involved to achieve mutual exclusion. So that is request, reply and release. Request is the one is the process who wants to enter into the critical section. That particular process will request all other processes in the network saying that I want to enter into the critical section with its own timestamp. Reply will be sent by the other sites or other processes in the network who is not executing the critical section, saying that we do not have problem you entering into the critical section. And the last one is release message. The release message is once the critical section is used, it should be released so that some other process can execute into that critical section. So these are the three messages that are required for synchronization via mutual exclusion. So each process will maintain a queue and it will store its timestamps into it. The assumption is that the messages that are delivered in FIFO order, first in first out order. That is why a queue is maintained. Then a timestamp is given to critical section request, and it is given with the help of Lamport's logical clock, which we have already discussed in the earlier class. Then Timestamp is used to determine priority of critical section request. Smaller the timestamps gets higher priority. So if timestamp is 1 and other process timestamp is 2, then which timestamp is smaller? 1. So 1 will get the higher priority and it will enter into the critical section. Now the execution of critical section request is always in the order of their timestamp. So whichever timestamp is the smaller timestamp will be executed first. Now let us look at this illustration and then let us map the algorithm. So these are the three processes that are into communication with each other, and we need to achieve synchronization for three processes. So initially a process P3 wants to enter into the critical section. So first what it will do, it will send a request message to all the other sites, that is process P2 and P3 with its own timestamp. Now this timestamp this timestamp is maintained in a queue. Each process will have a queue. This queue has two fields. One is the timestamp and the other one is PID, that is the process ID. TS stands for timestamp, PID stands for process ID. Now what is maintained in the queue of Q3? It says that at timestamp 1, process 3 is requesting for the critical section. Now the same queue contents are passed to process P2 and process P1, saying that the current request for the critical section is done at timestamp 1 by process P3. Now after some time, process P1 also wants to enter into the critical section, right? So P1 will also send request message with its timestamp. Now it will append its own timestamp to the queues. So see, initially at its own queue it will have timestamp 2 and process ID 1 because it is requested by the critical section is requested by P1, and this timestamp will be sent to P2 and P3. Now when it comes to P2, already the queue had timestamp 1 and PID 3. So its own P1's timestamp will be appended in the Q2's queue, process P2's queue, and at the same time timestamp 2 and process ID 1 also gets appended or concatenated at the process P3's queue. Now what happens is that a reply message, see, after sending the request, a reply message is necessary. A reply message is sent by the other processes. So P2, which is not involved in accessing the critical section, immediately sends a reply message that yes, you can use the critical section from my end because I'm not going to use the critical section in near future. Same happens with P1. However, P1 has already requested for the critical section, but it checks in its own queue that yes, I also want to enter into the critical section, so why should I send reply message? But it checks in the queue and checks that process P3 has timestamp 1, which is smaller one, and that means it has the highest priority. So I have to send a reply message. Hence process P1 sends a reply message to process P3. Again, for the process P1 also gets reply from P3 and P2. P2 sends same thing that I am not involved in the critical section, so you can use the critical section. At the same time, P3 also sends the process. The P3 also sends the reply. But then now if both the processes are which are requesting for the critical section are getting replies from the other processes, which one will enter? So for this there are two requirements to enter into the critical section. So what is the requirement? The first requirement is that in the queue, the timestamp should be on the top. The process which wants to enter into the critical section, that particular process's timestamp should be on the top of the queue. And the second requirement is that it should receive the reply messages from all the other processes. So here, which are all the other processes? That is process P2 and P1 if we consider P3. So P3 is getting responses from P2 and P1 and its timestamp is at the top in the queue. That is why the critical section will be allocated to process P3, right? Once the critical section is allocated to process P3, it executes it. After execution, it sends the release message. Why release message? So that some other process which is already requesting it can use that critical section and release it later on. So after P3 completes or process 3 completes its execution, it removes its timestamp from the queue, and now the updated queue is left with only process ID 1, which means that the critical section must be allocated to process ID 1. Now again here we will check for the condition that if it wants to enter into the critical section, two conditions are there. The timestamp of process 1 is at the top of the queue and it has received the reply from other processes. So it has received here reply from P3 and here it has received the reply from P2. So hence Q1 will go into the critical section. After Q1 enters into the critical section and utilizes it, it will release the critical section. And now the queue contents are empty. So here if you see, Q1, Q2 and Q3 are now empty, which means no process is requesting for the critical section. So this is the algorithm. So to enter into the critical section, first a process has to make a request along with the timestamp and its process ID, that it has to be maintained in a queue. Then after receiving the request message, a reply message needs to be sent to the particular process, and again that timestamp is maintained in the queue. To execute a particular critical section, two requirements are necessary, that a particular process should receive the message from all the other sides and its timestamp is at the top of the queue. And to release release the critical section, so whenever a process exits that particular critical section, then it has to remove its own timestamp from the queue and send release messages to all the other sites. So this was the algorithm, and the performance of Lamport's mutual exclusion is 3n-1 messages per critical section invocation, which means that by 3n-1, so n-1 request, n-1 reply and n-1 release messages. So again, so that is why this 1, 2, 3, so 3n-1 messages per CS invocation. Why so? So see, if I want to invoke one critical section, so this n is nothing but the number of processes. So how many number of processes involved in our illustration? 3. So 3 minus 1, 2. So for each critical section, 2 requests, 2 reply and 2 release messages. So we will go back and just see. So for each critical section that it wants to enter, there are 2 requests, 2 replies coming and 2 release messages that are going out. So that is why 3n-1 is the performance of Lamport's mutual exclusion algorithm. So that's it about Lamport's mutual exclusion. Thank you for watching this video. Please like, share and subscribe to the channel Simplified Computer Science Concepts by Professor Rutuja. For any doubts, you can post in the comments. Thank you for watching.